In this example, we're asked to find the regions of concavity for the function y is equal to 1 minus x squared over x cubed. Okay, so what we need to do here, as always, is we're going to take the derivative, but this time we're actually going to take the second derivative as well, because the second derivative is going to tell us where our function is concave up or where it's concave down. So from what we've just learned in the other section, so you imagine like whatever this curve looks like, we're going to maybe a section like this, and then maybe there's some other section that turns around. So the second derivative is going to be positive in areas where it's concave up, and it's going to be negative in areas where it's concave down, like in this section, right? So our process here is to find the second derivative of this, figure out our critical numbers, because those critical numbers are going to be potentially our turning points, and then we're going to make a number line and then determine regions of concavity from that. Okay, so that's where we're going here. So let's find the derivative like we always do. So we could use the quotient rule on this because it's already set up like a quotient. Or, what I like to do sometimes is actually just rewrite this. So I'm going to rewrite this as the product of two functions by just calling this x to the negative 3. I'm going to call that x to the negative, or sorry, this x to the 3. I'm going to call it x to the negative 3. So this becomes, in brackets, 1 minus x squared, and then times x to the negative 3. So same thing, but now we're multiplying, so we can use the product rule. It would work either way, though. But all right, so let's find, so step number 1. So number 1, let's find the first derivative. Okay. So using our product rule, so if we call this f, come on, pen, we call this f and we call this one g, then this becomes, so y prime, so the first derivative of, so this would be f times g prime plus g times f prime. So f is just 1 minus x squared times the derivative of g. So the derivative of g, we're probably getting pretty good at this, would just be negative 3 x to the, and since it's a negative exponent, right, so minus 1 is going to be x to the negative 4. So just careful on that one. And then plus, and now this is going to be derivative of f. Sorry, this will be g. So then g, so just x to the negative 3 times the derivative of f, which would just be negative 2x. All right, so that's it. So now let's just work on cleaning this up a little bit. So yeah, an easy, probably the simplest way to do this one would be to expand this term into this one and then just combine these just using our exponent laws. So let's do that first. So let's say y prime is equal to, so this first one will just be negative 3x to the negative 4. And then for the next one, it's plus 3. Negative times negative is positive, and then 3. And then just careful with your exponents. So this is going to be 2 plus negative 4, so like 2 minus 4. So this becomes negative 2. Okay. And then plus, and then if we combine these, right, we're really just going x to the negative 3 times negative 2, x to the 1. So this will be plus, or really minus, because I'm multiplying by a negative, so minus 2. And then with our exponents here, it's just going to be x to the power of, and then we add exponents. So negative 3 plus 1, we're now at x to the negative 2. Okay, well, that made things a little bit better here because those are like terms, so I can combine those. So y prime is equal to negative 3x to the negative 4. And then this just becomes, so 3 minus 2, so 1, or just x to the negative 2. Okay, so now that's looking okay. And yeah, we like this really is the derivative, and it looks like it does actually look pretty simple right now too. But the problem is if I want to find my critical numbers, then here, if I just write this out a little bit more, so y prime is equal to, this would be like negative 3 over x to the 4 plus 1 over x to the 2. It's actually kind of tough from this form to actually see what would x need to be in order to make this equal to 0. So what I'd rather have is I'd rather have like, some factors on the top and some factors on the bottom so I can see this kind of clearly, right? So I'm actually going to write this a little different. And yeah, here's what we're going to do. So instead of doing that part where I just kind of write it all out like that, what I'm going to do next is I'm actually just I'm going to factor out, what's common here. And what we do is we factor out, it's really always the lowest power. So this is x to the power of -4. That's my lowest power. So we're going to factor out x to the -4. Okay? And then see what we have left. So if we factor this out, what we end up with is, so I still have -3. But then what happens to this? Well, x to the -2 divided by x to the -4, right? Because that's what we do when we factor out. We're dividing it out. So then we just have to stick to our exponent rules. -2 minus -4. Well, that becomes x to the 2. Oh, I should write plus x to the 2, right? -2 minus -4 is the same thing as -2 plus 4. So there you go, -3 plus x squared. And now from here, I can say, okay, y prime is equal to, and then rewrite this as just -3 plus x squared all over x to the 4. And there you go. So that's my first derivative. And do you see what I mean? That now it's easier to see what would make this equal to 0, because then I just need to focus on what makes the numerator equal to 0, right? Where when it was written in this form, it was definitely more difficult to see what would make that equal to 0. So that's kind of what we're going for in this. All right, so that's the first derivative. But if we want to know the regions of concavity, then we need to figure out the second derivative. So now moving on to the second derivative, well, we got some options. I could do the same thing, right? I could use the quotient rule and, you call the top my f and the bottom my g, or call it -1 like we did in the first one. But you know what? If we're trying to find the second derivative, this was the second derivative, why don't we start from there? And then we can actually just take the derivative pretty easily of these individual pieces. You'll get the same answer either way. So if you want to do the quotient rule, fine. If you want to do the product rule by making that negative, fine. But I'm going to take a little shortcut. I'm just going to use this one. All right. So let's say the second derivative now. So second derivative. All right. So from here, so y double prime is going to be equal to, and I'm starting off, like I said, with this one. So bringing that -4 down, that becomes 12x to the -5. And then bringing that down, we get -2x, and then to the -3. All right, perfect. Now let's do the same thing we did in the last one, right? So if I want to rewrite this as instead something over something, then let's do that same trick of factoring out the lowest x. Okay, so let's factor out what we can. So y double prime is, and I look at my numbers as well, so 12 and 2, so I can factor a 2 out of that. And then x to the -5. And then when I start my bracket, what I have left here is just 6 now, because I took out everything else. And then what does this become? Well, the 2's gone, because I factored that out. So, but then this will be, so x to the -3 divided by x to the -5. We're really going -3 minus -5, which is like -3 plus 5. So this is x squared. Okay, now I'm just going to rearrange this a little bit. Y double prime is equal to, so this becomes, so the 2 still stays up in the numerator, so 2 times 6 minus x squared all over, and then we've got this x to the -5 jumps down to the bottom, x to the -5, or sorry, x to the 5 now. All right, so now let's find our critical numbers. So I'll just write CR for, or CN, I mean. So our critical numbers, where our second derivative is equal to 0. So I'm going to, instead of writing y double prime, I'm going to say 0 is equal to, and then our second derivative. So 2 times 6 minus x squared all over x to the 5. Okay, so what are our critical numbers going to be? Well, it's going to be where, the 1 as well, is going to be where the denominator is equal to 0 because they're non-permissible values. So where is that the case? So where x to the 5 is equal to 0, right? Like if the denominator is equal to 0, then we'll say, so that's going to be the case when x is equal to 0. Okay, so there's one of them. And then the other one will be when the numerator is equal to 0, right? Because when the numerator is equal to 0, then the whole thing's equal to 0. So we'll say, okay, it's also when 2 times 6 minus x squared is equal to 0. Okay, so if I start solving for this, I can divide by 2 on both sides pretty quickly and just get rid of that 2. So now I've got 6 minus x squared is equal to 0 still. I will take this x squared and just bring it over to the other term, or the other side of the equation, I mean. So now we have 6 is equal to x squared, and then take the square root of both sides. So we get the square root of 6 is equal to x. But I just made a little mistake. Not really a mistake, but I just kind of omitted something. One thing you have to remember is whenever we take the square root of something, there's actually two versions that come out of that, right? We really end up with the positive and negative version. So we actually have 2 critical numbers that came out of this. So in total we have 3, right? We've got x is equal to 0, and then positive square root 6 and negative square root 6. All right, so from here, we're going to make a number line. Okay, so there's my number line. And we're going to fill in, or actually mark down our critical numbers on the graph here. So I'll put 0 right in the middle. And then root 6, I'll put over here somewhere. So somewhere in there we've got square root of 6. And then somewhere over here we've got negative square root of 6. All right. So now the other thing I want to write down is the second derivative, right? So that was up here. So we write down the second derivative just above it, just for reference. So we had y double prime is equal to 2 times 6 minus x squared all over x to the 5. All right, so that's for reference because what we're doing here is we want to know, okay, is this thing concave down? Is it concave up? Down and up, or something like that, right? And we're able to tell what's happening just based on what the second derivative comes out as. If it comes out as positive, it's concave up. If it's negative, it's concave down. So let's just test out these different regions. And we don't really, even need to throw numbers in. We just need to know whether or not it's positive or negative. So let's do this. We'll say, okay, y double prime over in this area would be, okay, so this is around negative, 2.4. It's like somewhere in there, right? So if I try negative 3, it's something like that, or even larger if you like, then we can just think about whether or not really just even this factor up top, does this come out positive or negative? So negative 3. So this would be like, well, let's just try it for a second. So if we went like 2 times 6 minus, and then in brackets I'd have like negative 3 squared. Okay, so what that's going to end up being, right? Negative 3 squared, that's going to come out as 9. So I've got 6 minus 9. So this top thing's coming out negative, right? So this is negative. So far, what we've got is we've got negative, okay, because the 2 didn't really matter, over, and then the bottom, this is to the power of 5, right? So if I threw a negative number in for x, and it's an odd exponent, then that's still going to be negative. So I've got negative over a negative. So in this case, this is going to be negative over a negative. That's coming out positive. So what we can do there is we say, okay, what this is telling me is that we're concave up in this section. If you want to just write like a little line, just showing that's kind of helpful, right? Okay, so now let's try out this section here. So this would be a number like maybe negative 1, right? That might be a good one to try. So if you had y double prime in this section, so if we think we'd have like 2, which doesn't really matter, but you have 6 minus, and then you got like negative 1 squared. So this is like 6 minus, so negative 1 squared is positive, 6 minus 1, that's coming out positive. Okay, so that's coming out positive. So we've got positive over, and then negative 1 to the power of 5 is coming out negative. And then, again, the 2 didn't really matter at all there, right, for that. So this is going to come out negative. So in this section, we're going to be concave down because this is coming out negative. Okay, and then moving on to the next one. So this would be like maybe 1, right? We could try like the number 1 or any number in between there. And yeah, we don't even really need to write it out again. Just doing that so you could see. Y double prime. So if I threw positive 1 in there, that's going to be 6 minus 1. That's going to be positive. So the numerator will be positive, and the denominator will be positive, right? 1 to the power of 5 is still positive. Okay, so that's coming out positive. So then we're going to be concave up in this section. And then if I go past square root of 6, so we'll say, okay, y double prime over here is going to come out. So this would be a number maybe, again, like 3, right? So if we had 6 minus, and then 3 squared, that'd be like 6 minus 9. So in this case, that's going to be negative, right? So we're going to be negative up top. And then in the denominator, if this was, let's say, 3, like positive 3 to the power of 5, well, that's coming out positive. So this is going to be negative divided by positive. That thing's coming out negative. So this is going to be concave down. So there you go. We now know we've got a pretty good sketch of where our regions are going to be concave up or down, you know. So now let's just write this out. So we can say, if you want to do shorthand, concave up. And then we'll do this in interval notation. It's typically the way you're going to write your answers in this. We'll say, okay, so it's concave up. So it's in, this section and in this section. So we just need a way of stating that. So it's going to be from negative infinity to, and then it's going to be to negative square root of 6. Right? And then it's going to be changing from one to the other right at the negative square root of 6. So we're not going to say it includes, like it's not going to be a bracket like this. It's going to be a round bracket because it's going to be an inflection point in between those two things, right? So it doesn't include that point. Okay. And then it'd be unioned with, so there's the big U, or a cup. And then it's going to be unioned with, so then from 0, to square root of 6. And that's it. That's my region, right? Okay, and it's going to be concave down from, so it's going to be in these two sections. So that'd be from negative square root of 6 to 0. And then over in this section. So then so it's going to be unioned with square root of 6 to positive infinity.